right, I'm going to take a look at an example problem of modeling exponential growth, specifically using the e to the x function. So let's take a look here. We've got a fish pond. It's richly stocked with 150 fish. 5 years pass and the population increases to 5,000 fish. We're told that the population is growing exponentially according to the equation y equals c naught times e to the kt, and I want to estimate the population after 10 years. All right, now a couple of things going on here. First of all, I hope this formula looks very familiar. This is really the PERT formula, okay? If you remember, the PERT formula is A equals P times e to the RT power. P is the principal, it's where the C naught is in this equation. Of course, E is the number E, 2.718, so on. RT power, it's the interest rate as a decimal. So for example, a 4% interest rate would be 0.04. T is the time, okay? This is the general form of that. In other words, it doesn't just apply to money, it can apply to fish growing in a lake, or it can also apply to decay, things that are decreasing. Half-life problems, for example, we'll do one of those a little bit later. So anyway, in calculus, we tend to use this C naught e to the kt. I've told some of you about the n times e to the kt formula that a former professor, former teacher I'd worked with called the get naked formula. So anyway, lots of different variations. If you want to call these PERT problems, you can call them PERT problems. They're all in the same family. Anyway, the key to this problem that's different from the money problems is they don't start us off with an interest rate, okay? So you're going to have to figure out what that growth rate is, okay? Basically that K value, that often referred to as the decay or growth constant that we're trying to find here. And you should be able to do it with the information that they give you, okay? So a couple things to remember. That's your initial value. We've got time, we've got the growth constant. Should be able to fill everything in. So let's go ahead and do this. So you should be able to start off with the base equation. Y equals C naught times e to the kt power. And really what's happening here was, now you can really do this on a low level, and you can say, all right, we started out with 150 fish. So in other words, y was 150, and I need to figure out C naught, and I need to figure out these values. That was the initial value, so that's when t is equal to 0. So you don't actually need to know what k is, because you're going to end up having e taken to the 0 power when you multiply that out. Anything to the 0 power is just 1, and that tells us that C naught is equal to 150. Now, most of you have worked with the PERT formula enough to just know that the initial value is going to be C naught, so you don't really have to go through all of this every time, but you could, hypothetically, if you've forgotten that, okay? And by the way, if they don't give you something that starts out at year 0, you need to either change your time to start out at 0, so that's the initial value, or you would have to go through that process and substitute values in and try to figure out what it's going to be. So be careful. This is only in the initial value when t is 0. Okay, if they start you somewhere else, you're going to have to tweak the equation. All right, so anyway, we've got y equals 150, the initial value, times e to the kt power. Okay, 5 years went by and there are 5,000 fish. Okay, so I'd like to put 5 in for t, and I'd like to get a result of 5,000. Okay, so basically you just have to solve that equation, and this can be pretty quick. Couple of things here. We have an exponential equation here. Exponential equations, you want to have a base and an exponent and a result. 3 things, okay? I right now have a base, an exponent, a result, and a coefficient out here. You don't want to have a leading coefficient. You want to get rid of that coefficient. So divide both sides by 150, okay? And if you divide both sides by 150, unfortunately in this particular case we're going to get 33 1/3. That's the same thing as 100/3. So I think I'm just going to simplify this fraction down to 100/3, so I'm not rounding in the middle of the problem. And that's going to be equal to e to the 5k power. And then we can solve, okay? So this is an exponential problem. We're trying to solve for a variable that's an exponent, so we can use logs. We have a base e, so this would be the log base e. Remember, the log base e is the same thing as the natural log, so I'm going to write that as an ln, okay? The ln of the result is equal to the exponent, okay? Remember that logs are always equal to exponents. So I can take the natural log of 100 thirds or 33 1/3, however you want to write that. It's about 3.506. I'm keeping that value in my calculator. I'll write a few decimal places here just so you can see it, but really this should stay in the calculator. And that's equal to 5k. And then we can divide both sides by 5 here, and we can find out the k value. The k value is going to be approximately 0.701312, okay? And again, you want to go probably 5, 6, 7 decimal places or better. Try to keep it in your calculator. You could store it in a variable or trace back in your calculator and get that extended version of the decimal. Anyway, so our equation here is, we can really come back to the base equation. We've got C naught, which is 150, okay? Let me just take all this out. So C naught was 150. We've got e to the, here's our growth rate, okay, which is about 0.701312 times t, okay? It's a 70% growth rate. This fish population is going up very, very rapidly. It'd be great if your bank account did the same thing, which it won't. Anyway, we want to know the fish population size after 10 years, okay? So we're gonna sub 10 in there, and we're gonna figure this out. So I'm gonna do 150 times e to the, and again, I'm gonna use that decimal there that I have, and I'm gonna multiply that by 10, or I can just slide the decimal one place. And anyway, y is going to be approximately 1, 6, 6, and 3 more 6s. 0.667. AP lets you round to 3 decimal places. So 1, 2, 3, 4, 5, 6s. I think I'm 1 6 short here. Anyway, it's going to be that there. 1, 2, 3, 4, 5. Yeah, 5 6s. So it's going to be 166,667-ish fish overall after 10 years. Okay, so this population is much more than doubling over that time period. It's really continuing to explode. Okay, so hopefully that looks pretty familiar. Hypothetically, you should have done that in Algebra 2. Hypothetically, hopefully you did it again last year. And anyway, we're going to do the occasional problem like that again this year. So hope that little review helps get you back on track for that type of problem.